Thank you. Yeah, so my name is Jongboom. I work in ARM as a principal developer evangelist for Mbed. Mbed is our real-time operating system and an Internet of Things platform for building IoT devices faster. The Muska guys are, for example, using it to build a device where you don't need to figure out how do I do an RTOS, how do I do drivers, how do I integrate with TLS functions, etc. I'm a relatively newcomer to embedded development. I started doing embedded development about 4 years ago because I saw this IoT thing happen and I figured I want to build devices that run years on a battery. For me, I came from a web development background. Like, since I was about 9 years old, I loved doing the web, and what I really liked about that is that the moment that I write something and I go to my web browser and I refresh, it's there. It's this instant feedback loop, which is amazing if you're learning to develop for the very first time. And that's something that in web development, I'm smiling here at this point, but it's out of irony. In MCU development or embedded development, I don't feel any of that. So this was the very first product that I was working at. And all the stuff that I needed to get something to work is, well, a module and a dev board and an external debugger that I had to pay for. Only 5 hardware breakpoints. It's like for someone coming from a higher level language and knowing to develop that way, this is weird, this is mental. Why do I need a $300 development board? Why do I need a commercial debugger? Why do I need a commercial IDE? Why do I need a $5,000 compiler? This is absolutely crazy. So I didn't like that, but then on top of that, it's also incredibly slow. The feedback loop when developing on microcontrollers is not, I added something, I go to my browser and I refresh. No, it's I need to compile, I need to flash, and then I also need to get my device back into the state that I was just testing. So typical feedback loop from the moment I write a line of code until I can actually test that on an MCU might very well be 2 minutes instead of a couple seconds. And as we all know, developers cannot context switch very good. So for me, embedded development is really stuck in the 90s. It's on one end, it's because the languages that we still use, assembly, C, C++. On the other end, development tools that typically still only run on Windows. We see a bit of like happening where, for example, the ARM compiler now also runs on Linux, but where's my ARM compiler for my Mac? This is kind of weird. The debuggers are still very limited. I mean, sometimes they come on a development board now, which is a good step because you don't need to buy an external J-Link. But this feedback loop is still incredibly slow. And I kind of figured we had to live with that. Until, as a project I guess most of you are familiar with, I ran into the BBC Microbit. So this is a little tiny computer that was distributed to 1 million kids in the United Kingdom to teach them how to develop. And this is also an MCU, it's also an embedded device. It contains a Nordic Semiconductor MCU with only 16 kilobytes of RAM. But for some reason, the people that developed the Microbit managed to create a development environment which is far superior than anything that I've ever done on MCU development. So if a kid is programming this Microbit for the very first time, they don't see a compiler. They don't see C, they don't see C++. What they see is a web browser with, on the left side, a visual block level language, in this case where they say, I want to show the number on the LCD display, it just shows the compass heading. And on the right, they have a virtual version of their Microbit, the very same thing that they have in their hand. And whenever they change the direction on that thing, so in this case it's set to 14 degrees, they will actually print that on the screen. And this is beautiful because the feedback loop here is instant again. And it's great. I was teaching at one of the maker fairs in Norway, and I don't speak Norwegian. And I managed to actually explain kids of 8 years old that don't speak English and how to actually do stuff with this Microbit. And I think that's fantastic. And right after you're done, you hit the compile button, it gives you a file, you drag it into the Microbit, and then it runs. So that's still a bit slow, but the fact that you can do 90% of your development right here and test that out, and even do stuff with peripherals like the compass and the LCD display, that's brilliant. Now how they do that is because they have this pseudo language here sitting. So this block-based thing can either output to JavaScript, in that case we can run it directly in the browser, or to C++ and then feed it through a compiler and then have something that can run on the device. And while I like that, it's not what I wanted. I mean, I want to write my actual code the same way as I'm going to do it on the device. because I don't think the market is ready to say that you need to build your IoT device with this block-based editor. People love their C++. So do I. So I ran into a project already 5 years ago, which is called Emscripten, and Emscripten is used by originally targeted mostly at developers of game engines. So, for example, the guys at Unity and the guys at Unreal are using this, and it's a LLVM to JavaScript, and these days LLVM to WebAssembly compiler. So you can take C++, feed it through this compiler, and make it something that you can run in your browser. And I figured that's already pretty close to what I actually want in that case. I want to write my normal embedded C++ code, and then get something that I can run, for example, in the browser, because it gives me instant feedback. So let's take a look a bit at what happens if we actually write some C++ code and run it on a development board. So this is the Mbed OS Blinky example. So we define a digital out, which is an out port, on GPIO pin LED1, so that might be matched to a certain pin on your development board. And then, every 500 milliseconds, we toggle this LED. We either write a 1 or a 0 to that pin. So this is the user API, and typically someone who writes an application in Mbed OS is never going beyond that user API. So this is just the example for digital out, but there's also a networking stack and TCP sockets and LPWAN APIs and I2C drivers, etc. So this is typically what you see. So of course this is not what happens under the hood, because we have the C++ hardware application layer. In that case we see, well, we have a GPIO object and we want to write something to it, a value 1 or 0. Then we have a peripheral, so we're actually bus, where all these pins are on, and those pins are and that bus is generally memory mapped somewhere, in this case OX4, a lot of zeros. So the moment that a write comes in, we write to that bus. And if you look at how typically emulators are being written, it's that they emulate that bus. So they take the opcodes in your binary, they start running, and the moment that they see a write come in to this memory mapped address, that's the moment that they intercept it, and then they toggle a virtual LED. And this is a traditional way where you would hook this stuff in. So that was the first thing that I figured we can do. The downside is that you make something that's very, very specific for a single board. And it's kind of weird for me, because we already have the C++ hell and we have the C hell, and typically no one is going to actually poke into the bits here. So the next thing that I figured, one way we can just create a fake C++ hell. The only downside is what we ran into there is that it requires you to completely rebuild the C++ hell in something like JavaScript. So where we actually put it is here. So whenever a GPIO write is called, instead of going to the bus and actually writing a 1 or a 0 to that, that's the moment we just intercept it and do something in there. That is a really ugly emoji. That works actually surprisingly well. So this is something that we have today. So this is what it looks like. You have on the left, you have your code. You have a compile button. At that point, it takes all of Mbed OS, cross-compiles it through Emscripten, hooks in a couple of places where you say, well, if a write comes into a pin or a read comes in from a pin, that's the moment that I feed that data back. If something happens on the UART port, then we feed that back again. Now I have something that can run completely in JavaScript, so there's no server component here, and run my embedded application. I think it's pretty great. We have a couple more examples coming up. Of course, there's some challenges, stuff that we can do in a real emulator, like fast models for Cortex-M devices that we can't do here. There's no interrupt handling because we can't really simulate interrupts. An interrupt runs at a higher priority than everything else in the microcontroller, but in a browser everything runs at the same thing. There's only a single thread. I can't spin up multiple threads in a case, and networking typically is a lot harder, because in here I can just open typical sockets, and that's something I can't really do in a browser. So around networking, we figured something. There's a couple of places where we could hook in the simulator. Typically an emulator does it on a hardware level. So a moment that a write comes in over UART that says open a socket, that's the moment that someone jumps in, or maybe you have an actual Ethernet driver that is then emulated or forwarded to something on your computer. I figured it might work better if we hook into the networking primitives in Mbed OS. So we have TCP sockets and UDP sockets, that's the underlying layer. And on top of that we have DNS handling, Mbed TLS to actually do HTTPS requests. So we hooked that in against a little Node.js daemon that provides sockets in the browser. So the nice thing what we can now do is that we can take, for example, our complete HTTPS library and actually do an HTTPS request in the browser, in the simulator, and actually see this handshake happening. So the browser, we don't use any of this browser stacks. So stuff where we don't load the right certificates in, or we don't load the right CAs in, is stuff that we can handle straight away in here immediately. And for me, I was working on our HTTP library on a plane from Italy back to the UK. And I was writing this code in the plane without having a physical device. And the moment that I kind of figured, okay, this kind of worked, I went into the lounge at London Heathrow, hooked up my development board, plugged it in, and this stuff worked. It was just brilliant. It's a fantastic feeling. The same thing can actually happen for LPWANs. LoRaWAN is a low-power, wide-area network. It's a non-IP network. But we do something similar in there, and let's say that in our LoRaWAN stack, that's something we keep as is. So all the encryption, the join procedures, the moment that we do key exchange, that's something that we keep. But the moment that we write to the radio driver and say, okay, at this frequency, send out these bytes, that's the moment that we intercept it, and then we send that directly to a network. So what we have here as a demo is, on the left we got the simulator. On the right we have a commercial LoRaWAN network server. So this is something we didn't modify, because we wrap the packet that we normally send over the LoRa radio into something that that network understands, sees that it comes from a real gateway. We can see that when we refresh this page and we start, it actually does a join with the network. It sends something back. That's what we pass back into the networking stack, and now also on the embedded device we join. And the moment that we send the value, in this case 32 degrees, we get that payload. And this all goes encrypted over the line. There's nothing special we were doing here. So we're doing this together with the network server, with the network provider now on building an actual network simulator based on this stuff. And that's something that's really hard to do traditionally. Bringing in new components works in a bit of similar way. So, for example, for the LCD display that we have here, we use the font library and the layout library, everything that we normally do there. But the moment that you normally send the display buffer over SPI to the physical peripheral, that's the moment we dump it into a canvas. So these drivers are 98% the same. And as you can see, even the timing is accurate. And this is an example that I just got from the Mbed website. So the simulator right now can be run in two ways. There's an online version, which is, I think, really cool for testing, for educating. It's a really nice way of showing people how embedded development works, what kind of events can come through, and it gives us instant feedback loop, just like we have with the BBC microbit. And the second thing is an offline compiler. So you install the compilation toolchain. After that, you just run Mbed Simulator in any Mbed OS project, and that will start at the simulator and actually keep running. So this is Mbed OS Blinky. Just literally run this. It opens a browser, and here's your project running. Microtensor, which is a deep learning library for microcontrollers that we also built, can also be simulated this way. So we run Mbed Simulator, and now it gives us a deep learning model, in this case the MNIST dataset, which was taken from TensorFlow, cross-compiled to ARM, Cortex-M, and then recross-compiled into the browser and telling us what the number was that we had here. So this is super Inception. The last cool feature, I think, is this whole way of cross-compiling your application from one language to JavaScript is something that has been going on in the web community for a very long time. People love doing TypeScript and then cross-compile it to JavaScript. So one of the things that is in all the major browsers is this thing called source maps, where you debug your JavaScript, it shows the original form of your source code. And that's something we can abuse for C++ development here as well. So if I have, and this is the online compiler, if I have an application that runs, in this case, whenever I press the button, it triggers an interrupt and then enables an LED, I can just hook up the normal browser debugger, and on my debugger tab, I see my C++, I can just throw in a breakpoint, and the moment that an event toggles, I see that in C++, so don't even see the recompiled code, which I think is really cool and really powerful. It has some stuff not like stack inspection, but for basic step-through debugging, it's already there. So, as a recap, I think embedded development is still an absolute pain in the ass. I don't like it, but I think that if we do proper simulation and actually has the opportunity to make it less painful, have students actually have a little bit of joy in embedded development. We're actually using this in educational programs already. With clever positioning of where you do the simulation, we can even do stuff where we typically require a lot of hard work, like networking and LPWANs, or even simple peripherals, and actually help create something that is going to go to market faster and actually has a way of less bugs, because it's something we can already run on a computer and, for example, run our tests in that case as well. So go to labs.mbed.com. There's the online version of this. You can just take it in any browser. And it's an open source project, Apache 2 licensed. So if you want to get involved or you want to use it in education, please let me know and we'll do everything in our power to help you with that. Thank you.
Thank you. Do we have any questions for Jan?
I know, it was perfect. No questions.
Okay. So are you planning to have a support for custom boards as well? So if I want to build my own board, I just pick a microcontroller and whatever. Are you planning to do that as well, or is it just developing boards?
I think I would like to do something similar, and especially for products. Because a product is a core plus a bunch of peripherals, and that's something that people want to develop for. However, it needs to be, I want to keep this Mbed OS C++ hell, so as long as it supports that, that's free. But I need some abstraction layer that we can hook into. But yeah, if we got some more time, I'd love to do something like that.
Thank you.
Yeah, does that system run under Ubuntu, by any chance?
This runs on Ubuntu, yeah.
Yeah.
Ubuntu, Mac OS, Windows, and online.
I've had the experience with the code clubs running some of the stuff, and you have a big problem trying to get the scratch users.
Yeah. So typically, I think actually for if you want to use this in for kids education or in even in normal education, the only thing you need is a browser.
Yeah.
So no dependencies, no nothing. Yeah. In addition, our Mbed OS compiler, our Mbed compiler online, also runs completely in the browser. And then our board mounts as a USB mass storage device, and you can just drag your file onto that. So it gives you the simulated environment on one end and the real compiler on the other end, and you don't ever need any drivers or anything like that. All right.
Any more questions? So I have one question.
Sure.
Security.
Security.
Are you able to model some of the security features that Mike was talking about, if people want to try using them in their applications?
Not yet. If you want to do that, we have fast models, and fast models actually model our actually underlying cores. So our fast model for Cortex-M 33 actually has support for trust zone right now, so you can load it to that, and that's something you can experiment with. It's a bit outside the scope of this project, but that's something we have.
Okay,
All right.
thank you very much.